Our next keynote speaker is Simon Thompson. So he's a professor at the University of Kent, and many of you probably know him from his book, The Craft of Haskell Programming, and one of my personal favorites, Type Theory and Functional Programming. So yeah, please, thank you very much for coming here, Simon.
Okay, thank you very much, and thank you for the invitation. It's the first time I've come to an event like this, and I've really enjoyed it, so thank you. Okay, so I'm going to talk about lazy interactions, and it'll have an aspect of Back to the Future, which I'll explain in due course. So it's going to be a gentle discussion of a few bits of Haskell code. So it'll be slow, and I apologize if you're familiar with all of this, but I think we can learn some things by looking back at perhaps stuff we're familiar with. So in one of the functions in the standard prelude and in system.io module is a function interact. And it takes a function that takes strings to strings and turns it into an IO program, something in the IO monad. And the way it works is very simply, you get the contents, get the input, and apply the function to the input, that gives you the output, and you stick that on your output channel. And there we are, a two-line function. And that's at the heart of what I'm going to talk about the rest of the time. So what it's saying is, the output of a program is a function of its input. So, fine, that's something that we're entirely aware of. And we get, with a function like this, we might think these are strings, which I'm formatting in a slightly more elegant way. We have inputs on the left-hand side, 3 and 23 and 45 and 67, and they generate that output, those pairs, 2, 23. It doesn't matter really how I'm computing those, so I will show you the code a bit later on. But we're seeing the output as a function of the input. But of course, that's not the point. The point is, this is an interactive program, so what we're really interested in is that. We're interested in how, as we type bits of input, we produce bits of output. And so that makes things a bit more complicated. What we had here was, we could see there's the output from that input, but as we see it, if we're thinking of it interactively, it's going to behave a bit more like that. And so the interaction, what this means as an interactive program is how input and output are interleaved. And in this context of the interact function, interleaving is going to be determined by lazy evaluation. So at least the context to this is lazy evaluation. Having an interact function like that in Erlang or in OCaml wouldn't make any sense. It only makes sense to write a program like this, as a function from input string to output string, when we've got lazy evaluation. So that's the context. And in a sense, you could say this kind of encapsulates the essence of laziness. Because to think about what our function is going to mean as an interactive program, we don't care what it does with the whole of the input, a total string, a properly terminated string. We care about what it does with things that are terminated by undefined, things that are terminated by we don't know what is going to happen here yet. But semantically, that's undefinedness. So the point about this sort of approach is it's saying the behavior of this function on partial lists that are terminated by bottom, determines the whole interactive flavor of this, the interactive behavior of this program. So as I say, that's as it were the essence. And so the message, just of this introductory bit, is to say lazy interactions are determined by behavior of functions on partial data. They're very different. We're not talking about sequences, we're talking about a single list, but we approximate the input so far by a list terminated with bottom. Okay, so that's our context. And let me show you, if I can get this to work. Let me show you, is that visible? Can you read it at the back? Okay. So let me go into GHCI. And I can show you some examples. So we've got interact. We can write a function like this. Ooh. Unline, no, not unlies. Sorry, this is the problem with map. Reverse. And lines. So I've written this. What's it do? It cuts the input into lines. It reverses each of them, and then you'll see that it does what it says on the tin. Now, the only sad thing about this is that the only way I can terminate it is because when we defined interact in that way, the whole of the input gets given to the interactive function, so we can't escape from it without escaping from GHCI. So it's a very nice way of writing top-level interactions. They don't play perhaps so well if you do them inside a interactive shell, but never mind. Let's look at another example. It's a similar one. What do we do? Unlines dot map. Let's just map ID. So what we did the last time, for each line, we saw the line followed by the line reversed. So what we should do here is just see the same thing, but without the lines reversed. Oh, thank you. Oh, help. What's happening here is it's echoing every letter. Even though I'm applying lines to it, mapping ID and then applying unlines, it's just echoing every letter because the input isn't buffered. But surely the fact I'm dividing it into lines has to make it cut it into lines before it can map ID. Well, no, because it's lazy evaluation, and it's so delicate. I think the message of this is, even if you write a one-line program, it's often difficult when you write it like this to get it right. So let's go back to where we were. That's demo. So if you're writing these programs by the seat of your pants, as it were, you're thinking, I'm just going to write this function from strings to strings, you're going to get a difference depending on whether you write your program like at the top or at the bottom. Because, of course, it doesn't matter if you give that program a total list, it's going to give you the same answer. It's going to say prompt and then... but if you give it a partial list, in the first case, you'll be able to produce the prompt. In the second case, as you give it a totally undefined list, in the second case, you can't. So, it's another example of why laziness, why the behavior on partial lists is so crucial here. So in that sort of example, ugh. Now, of course, you can also do, in Haskell, you can also do this. You can put a tilde there, and that turns the pattern x:x into an irrefutable pattern. And that has a slightly different semantics. So we are getting, it's a bit like Prolog. You have all this lovely high-level stuff, and then you start using cut, and it turns into this disgusting mess of it's a bit like that we insert a tilde for irrefutability will change the interactive behavior of that program. You could say it's a bit of a problem. So I think the solution to this is not to try and do it seat of the pants, but to try and build, this is the Haskell answer is, let's build a model of interactions and think how to combine them together. Okay, so that's what we'll do. And I said there's an element of Back to the Future about this. What I'm talking about, in fact, is something I talked about at a meeting in Austin in 1987. So I wanted to present you with some work from the sort of prehistory of Haskell. Haskell was devised in 1987 as a reaction to Miranda, the existing standard lazy language, which was proprietary, and so people couldn't extend it in the way that Haskell has proved has been a very nice model. And in 1987, Tony Hoare and Edgar Dijkstra were both at UT, and there were 5 or 6 week-long schools to talk about the art and science of programming, bringing leading scientists together to disseminate what was learned about theory and practice of programming. And there are a number of these, and one of them was about declarative programming, and so there's one about lazy functional programming. Lectures interposed with programming sessions conducted with pencil and paper. This is very Dijkstra-esque, attended by the lecturers. Major topics included data types, polymorphism, recursion, induction, list, domain theory, program synthesis, blah, blah. So this was 30 years ago. There's a nice, and this is you can see it's 30 years ago because the report is kind of pre-web, right? It's just a scrappy photocopy. There was a nice coda saying, this institute elicited particular enthusiasm among a group of UT graduate students who circulated among themselves a petition calling the department to make functional programming a more visible priority in the department. Ha! The recruitment of faculty engaged in research in the field. I don't think that happened, at least at UT, but it was interesting to see that. Now, this isn't, and there were books produced for this, and one of them was where the work from here is reported, was on research topics in functional programming. And the reason I wanted to do this was not because I didn't have anything new to say, but it's sometimes we can learn something by looking back at what we've done in the past or what other people have done in the past, but also thinking about what changes there have been in the intervening time. And I suppose partly the point I wanted to make was a lot of the ingredients that we have for doing functional programming now, we had 30 years ago. So I suppose, is what I'm going to show you, does it still make sense now? I hope it makes sense, but it's not necessarily how we would do it now. With retrospection, we can think, okay, we could take this work and do it in a different way, more polished way. How can we bring it up to date? And I suppose it might also point, are there any missed opportunities? You know, the things have gone in one direction, could things have gone in another? So that's what I'm going to show you. There are 2 aspects to this which I'm not going to talk about. It was Miranda code initially, and I had to transliterate that from Miranda into Haskell, but that was pretty much routine. You had to change, excuse me, some capital letters had to become small letters, and a few minor things like that. Pattern matching in Haskell is different, so there are some places where, and this caused me some grief in doing this, there are places where we need to insert tilde, because Miranda had irrefutable pattern matching. Miranda had irrefutable pattern matching by default. Haskell has refutable pattern matching by default. But not much else changes. And also, something I'm not going to talk about is that there's some programming stuff, but this was a time when people were thinking everything we did ought to have some semantic underpinning. So there's a lightweight semantics for functions that work with partial data. It's a kind of lightweight denotational semantics for a portion of a language. And there's some proofs, I made proofs that sequencing work. The sequencing combinator, which we'll talk about in a minute, actually does sequencing. So the set of traces of the sequencing combinator are got by, and it's a bit fiddly because you have to think about how termination works, how partiality works, and maybe that's a lesson. as to why this isn't such a good approach, not such a robust approach in general. But the paper, all this stuff is on a GitHub repository. There's the paper, there's another version of the paper. I'll put the slides up at the end and the code. I'll put the link up. It's my GitHub ID is Simon John Thompson, so you can find it under there. But I'll put the link up later. But anyway, so let's look at this. Let's look at what we've got, and then think how we might do things differently now. So what I built, what we talked about, we had these things, these functions, which went from input, pair of things, to a triple. At an input, A and B were in one of Miranda's rather peculiar syntactic choices was that type variables were star, 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 and so on. So you didn't, type error messages quickly became incomprehensible. So it's easier to have A and B. So you take you take the input and something of some type, and you get back what's left of the input, something of another type, and some output. So those are the things. And in retrospect, though I'm not sure this was articulated at the time, there are two ways of viewing these things. And this is where, I knew about category theory, but I thought I'd left all that behind when I stopped doing mathematical logic and I started doing programming. So I didn't think about Kleisli composition or anything like that. Though perhaps I should have done. So one way of thinking of these things were functions with I/O side effects. They take some input and A, and they as it were, the input to the function is of type A, the output to the function is of type B, and there's some I/O going on at the same time. So that's one way of thinking of them, but I realize there's a second way of thinking of that, which is a sort of twist on that, and that is that these are interactive, call them interactions, and they have a state, and that state changes between steps. So you start off with a state of type A, you then have a state of type B, you then have a state of type C, or whatever. So that state can change, might change the value in there, but you might also change its type as you evolve. So these two things, and there's a sort of picture which you can imagine. You've got this something going in at the left, coming out at the right, but you've got stuff intervening because you've got inputs coming in and outputs going out. So that was the picture. And you've got these two, and so when you look back, things are messier. Perhaps there wasn't a single view of what was going on. They could be functions with side effects. They could be sort of interactive things where the state changes. And both those, I realized that both those models are sort of implicit in some of the combinators that we got. So just the basic types. In order to finesse the, I'm just thinking of input as a list of strings and an output as a list of strings. I don't want to think about raw input character by character. So I'm thinking of input as being a list of strings. And then we have interactions. We also have conditions. So conditions aren't simply conditions on the state. They can be conditions on the input as well. So it's sort of like, it's a bit like a parser type with a state change in there. I suppose that's another way of thinking about it. And then there are various ways of putting these things together. So I've omitted the up and down things. You can imagine what there is. There's a sequencing, there's a parallel combinator, well, pseudo-parallel. There's an alternative, the while, there's a looping combinator. And the combinators work in such a way that everything is well typed, as you'd expect. One of the things that sort of comes out of thinking of these things as state is that this thing in the right-hand corner, this pass on L, you're going to do a bit of interaction with the thing underneath, but you just want a variable, and you just want to pass it on to the state that follows. And so this sort of plumbing comes in, which is kind of reminiscent of what people have done with arrows. So you can see there is this sort of mixture of things going on. But the key combinator, of course, is sequencing, and here's the definition. We've got two interactions and an input X. What do? We apply the first interaction to X, and we get the rest of the input new state and output. And then what we have to do is somehow do that output and then call the second interaction with the rest of the input and the new state. And what make output does is it adds that piece of output to the front of the output of the whole thing. So there's our, as I said, the Haskell wasn't going, it's nice short bits of Haskell, as befits 5:30, and the barbecue is ready. So I'm not taxing you too much. Fine, so I did all this, and of course I typed that into, I tried my examples, and they failed. Because we need some irrefutability. And what's more, we need some more irrefutability. Because think about it, what we need in both cases, we want to delay that pattern match. We want to push. We don't need irrefutable patterns. We can do them by heads and tails, or appropriate deconstructors, which we push into the right-hand side. But this is just more elegant. But we want to make sure that we put nothing in the way of constructing output, because what is output on the screen is what comes out of this third component of make output. How else could we get it? So we allow things to be put on the screen without forcing the thing to which we apply make output, which is the application of inter2, that's the second interaction, and also the local definition of which gives us the rest and st. We can be as lazy as possible. And with that, it all works. And then we've got alternative, and we get nice definitions like this. So while is just defined, we can define in this sort of almost algebraic way. So while you apply alternative to the condition, and then if it's true, you do the interaction and call the recursive function recursively, otherwise you do nothing. So we get these nice ways of structuring our interactions. And well, I also discovered there's this thing called, so if you look at this so far, we've got a miniature imperative language, effectively. We've got a state which we might manipulate from positions to positions. But then there's this funny thing, which was called pass parameter. Oh, what does that do? That takes an interaction, then it somehow gets that thing, which is the output of the first thing, and puts it into B, which is the input to that function. Look familiar? This is where bind comes in. So there were some places where you need to do this. But I guess it got called pass parameter. Why not? And there are some variants of this, because you might, in fact, there I'm passing B into an interaction which starts with an empty state, but it often got used where you pass B in twice. It determined the new interaction, and it was the input to that new interaction. So it was providing two things. You sort of escape, call your function external to the program, but then you keep feeding that state through. So again, you could argue, he really doesn't know how to design an API here. And there are overlapping functions, overlapping types. Maybe that's a bad smell. Maybe that tells me that what I'm doing is not very good here. But it did what it was supposed to do. And there are some primitives which you can imagine are straightforward. There's a thing called apply, which turns a function into one of these interactions. And there is something to write and something to read. And there are things like forget, turn a state into an empty state, start, so turn an empty state into a state with some values in it, and change. And there's a thing called wait, which we'll meet in a second. And then there is a function which we have to write now. If we're doing this in Haskell, what we have to do is turn that interaction into an IO, thing in the IO type. In Miranda, there was you had to turn interaction into a string-to-string function, and the runtime supported interactions in the interpreter. So you could do an interaction, it would allow you to read the input as far as it went, you could interrupt it and then drop back into the interpreter. And I guess one could modify GHCI to do that, but not with the current definition of interact. Okay, so there's some primitives. And they look, as you would, I'm sure as you would imagine them to look. Apply, you just apply F to the state. Write, you just stick something in the output. Read, you take the tail of the input, and the head of the input is what you've read, and the tail of the input is what remains. And run, you effectively interact in that way. I wonder, you could make that irrefutable. But there's an exercise. Yeah, it would be possible to stick another tilde in front of that. Not sure you need to, but anyway. Okay, so there are primitives. So we've got this model, and that allowed us to control what was effectively uncontrollable. And let me do a demo. Let me show you a few things. Actually, no, let me not show you. Let me show you some slides first, and then I'll show you a demo. Because I wanted to make some point about style. Because I guess there are different ways that these things might support some interaction. Here's a function to do copying. What you do is while true, you read in and then write out. So there we are, we just copy. But we've got a nice model that we don't have to think about the pattern matching. We've got while, we've got a condition, and we've got a primitive action that reads in and writes out. And that's, if you like, entirely in this little imperative language, entirely within the combinator language. There's an alternative, though. We could do something like this. We could write it recursively in the using recursion. So we could be somewhat meta-circular, if you like. We can have a little meta-circularity. We can use recursion in Haskell to give us that repeated behavior. Or we can just say, here's an outright definition of copy as an interaction. So there's that. This model supports those different ways of dealing with things. Okay, so let me see. I mean, we can have a look at those, and then we can see that they'll work. Look. I go into here. Let's go to GHCI, and we need to go into examples. And then let's run. What should we run? Copy. Of course, I need to run it with a starting state. And then we're getting what I type comes out. And the copy function I'm looking at here is, where is it? This is the recursive one. So copy here on the left. That is the one which is reading in, writing. But I can also, do a similar thing. I go into GHC again, and then I can do run. And here I could do while const true, read write. Yep. And I've done this again, sorry. The starting state, and then there we get the same behavior. So we're seeing there we've got an explicit definition using while and const and so on. So we've got those different styles that we can use to build these interactions. And going back into prehistory, as it were, this was a reasonable way of writing interactive programs in Miranda, which had this model built in. It was also prefigured in the early versions of Haskell, which I think I should have done my homework. One of the early versions had 3 different I/O models. it had a continuation model, it had a variant of this. Can't remember what the third was. So it took a while for Haskell to evolve. I think I can't remember exactly when, perhaps about the mid-90s. Certainly by Haskell 98, there was monads were there as the one true way of doing I/O. But up to that point, I mean, certainly continuations were seen as a viable alternative, though the programming there was a bit of a nightmare. And so I adapted this model for what was going on in Haskell as well. But let's get back to the talk. Whoops. Where's my talk? Help. There we are. So as I say, there's a little bit, you've got this choice. Do you do things just within the combinator library, or do you do recursion? So where I've kind of wired recursion into the definitions of the combinators, or do I do something in the meta language, as it were? Here's an example. This is a function which doesn't do any prompting, so you've got to know what it does. It takes a number, positive number, and then it reads that number of numbers. And this is a version that uses this sort of state idea, this state that grows and shrinks and so on. So let's just track through this. What's going on? We get an integer, so our state is now the value which is the counter. We add a value which is the sum so far, and then we go into a while loop, and what we do in there, we're adding a null value. This is where we're going to get our input. We get our input, and then we put our input into our counter and sum. We're combining it there, taking one from the counter, adding the input to the sum, and then we wait, and reasons I'll show you in a second, and then we recurse. So this is a model which is entirely within the little language, the combinator language. But it's a bit of you need some way of dealing with this state that grows and shrinks in practice. And the way that we finished up doing it at that time was to build an abstract data type. So you have an abstract data type which has operations which do the things that you can see going on here, but does them on a state that doesn't change. So that's horribly messy. This is not intended as a model of good code in any sense. But it's showing you that this model of things that have side effects, where the state grows and shrinks, will allow you to write functions like this. On the other hand, you can write things like this. So you can be a bit more metacircular. You get a number, and then you pass that number in, so as it were, you bind. And what I'm doing here is I build a list of n add nums, and I sequence them together. So I can actually build this inline the code for the program, if you like. So a very different style. So you can see these two styles being supported, whatever reason. Anyway, fine. I don't think I'll show the demo, because I think I wanted to go and talk about some stuff. So looking back, what is there to learn? First thing is, all the ingredients that we use now were there. We're using higher order functions, lazy evaluation, pattern matching, actually hardly any algebraic data types in here, but there could have been. Those were all the things that were there. Well, almost. Miranda had no lambda, so no let. So you got a variant. You had to if you wanted an abstraction, you had to name it, and that was a bit of a mess. But apart from that, equality was overloaded, but there was no show. So there are some things, you have to change a few things to get this to be valid Haskell. But it's pretty much there. So there were very few established design patterns. There are bits of monads in there. I think you can find some bits of applicative. There's some ideas from arrows. There wasn't an established, so I think the model of programming then was very much use these nice features, use the fact you've got functions as data to build rich combinator languages which express the particular piece of the domain you're interested in, but there was nothing to give you structure. There wasn't the idea of monads. There wasn't where you had binding very, very clearly, giving you naming, to allow you to build complex computations. There are bits of arrows in there, but I guess it's fair to say arrows have been... Not many people use arrows. They're not in Haskell book, I don't think. It's been one of those things that's been interesting, but has perhaps been a sideline. Whereas monad and applicative have clearly won out as design patterns, which are simply there and are completely associated with where Haskell is at. So if we were doing it again, we would, I suspect, build a monad. We might have an applicative and then build something monadic on top, but that's what we'd have. There's another approach which I think people were just not thinking about at that point. You can see this as a shallow embedding of an interaction language. So you've got a collection of interactions. What you have inside this type is, for each interaction, abstract interaction, there is a function that represents it. So a shallow embedding. You've got a piece of data in here that represents what's outside there. But it doesn't represent how it's constructed. So what if we were to make this a deep embedding? That would mean something of the form like this. We would have a data type that represented interactions. We could then do different things. We could interpret them, but we could also optimize them. We could also do transformations over them, and so on. I think that's something that has come into the Haskell programmers' armory in a way which, so thinking of DSLs where you can take a representation of what you're representing rather than just representing it and use that to good effect. I think that's something that we would clearly, I think we would do differently. But it's interesting there, can we do that easily? I've got this data type here of interactions. These are just untyped interactions. I'm not type checking those interactions. I guess I might be able to do something with GADTs, which would allow me to more faithfully represent the types that there are in the interaction library within the representation of those interactions. But as things stand, that's not the case. So in just vanilla flavored Haskell 98 or whatever, we would find it difficult to reflect that typing in a. So those type and all the fact that we can build values at the type level, that allows us to do a whole lot more stuff that might mean that we would present this in a completely different way. Oh, I've just said all that. I didn't really, yeah, okay. So I think, I guess a thing that came over quite strongly to me is the fundamental scope of values hasn't changed. What values were there in Miranda? Well, there were functions and higher order functions and algebraic data and abstract data types and numeric types and equality and so on. There's nothing new in Haskell, really. I mean, there's bit strings, but there's nothing essentially new. We don't have objects, for example. So nothing has changed in the sense of what data we use to do our representation, to do our computation. That hasn't changed. What has changed is the way that we use types to ensure correctness and to ensure higher fidelity between the thing we're modeling and the model that we build, hopefully. But it's striking, I think, that those, the set of values is just the same. Whereas if you were to go back 30 years from 1987, what would that be, 1957? What types were there in 1957? Yes, machine words. So it's intriguing how much things moved up to that point. The functional programming, functional programming was moving at a very rapid rate up to the late 80s. And there's lots of excitement. The 80s were a bit like now. Loads of people thought functional languages were the coming thing. It didn't happen. Whereas I think now it is happening quite seriously. But it's interesting that the more recent developments have been around types, around patterns, design patterns, and so on, but not so much about the fundamental data structure. One thing that occurred to me, there was lovely work done in the late 90s by Thomas Hallgren on functional widgets. So this was taking this model of stream processors and building a GUI library on top of it. It's really lovely. And an early version of an early predecessor of Agda. I can't remember, it was Alpha, I think it was Alpha, perhaps Alpha, was built using fudgets. So this model of processing streams was shown to be entirely viable in a much more realistic context, not thinking of strings of whatever going to a command line. So maybe it's time to look at fudgets again. They were, as I say, the main development I think was between 96 and 99, but it's maintained and there's the link. So if you want to play with them, they are there to play with. So I guess I was thinking, how do all these other things impact on us trying to build things now? These were the various directions I was thinking of. Nice, interesting to think about this sort of stream processing in the now that we have concurrency on the hardware platforms we work on, but also inside Haskell itself. Clearly, we've had huge developments in compilation, in libraries, and taking up the message from the talk yesterday about adoption of functional languages. I think one of the things that is clearly key, not people, if you look at the research in this, generic research on language adoption, libraries, communities are much more important than tools or speed of compiler or whatever. Being able to do what you want to do and get help when you fail to be able to do what you want to do are some of the key things. Okay, and I'm going to terminate just with a few things. Things that I think we thought were going to happen that haven't. I think we thought routinely, 30 years hence, everybody would be verifying everything. We knew we could write logics for functional languages. We'd just be writing, everything would be proved correct. And everything would have a semantics. Denotational semantics was on a high. People were talking about operational semantics. It always seemed a bit dirty. Denotational semantics was this beautiful model, and our languages will just be defined in terms of semantics, and we'll derive compilers from the semantics. We're getting there, but a lot more slowly than we thought. I think people envisage the end of programs as text. That would be lovely. If you want to build tools, wouldn't it be nice if all we had to think about were ASTs instead of people's peculiar layout fetishes, which you have to indulge if you're to build a refactoring tool. And what also happened, I think the reason people were really excited, and I think the reason that I think it was the US Office of Naval Research supported this year of programming, was that they were worried that they were getting to this sequential, they were going to hit the wall sequentially. And people were saying, we need special purpose parallel hardware, and functional languages are the things to run on that. Well, didn't quite work out like that, but anyway. But again, we're now moving to multi-core chips, and some languages fare much better on that than others. So it's, as I say, it's given me a chance to think, and it's interesting to think about what we've had for a long time, and what Haskell has brought, some of it quite recently, to the table, what it is that makes Haskell special. And I think it's a number of these things. Everything on that that slide is there. Neil was telling us about lightweight tools yesterday, and those just get used. There's a fantastic community, such as yourselves. The libraries are there. Things like Monad as an API, which helps shape our insights, our designs, and compilers that really are pretty damn good. So I think all those things are there, despite some of these other things not. So But interesting, nonetheless, to think that the way that we built things 30 years ago is not that unlike what we're doing today. So I think it was that combination of continuity and change that it was the message I wanted to give. And if you want to look at the code and play around with it, it's there. So thank you very much.
Yeah, there's time for some questions.
Hello.
Hi.
So, I think on the topic of the things which didn't happen, I don't entirely agree on the special purpose parallel hardware.
Right.
Because this thing is happening currently with AI. TensorFlow by Google and those TPUs which they have recently announced, they are essentially that...
No. What I was meaning was, sorry, I was meaning that this was why in 1990 everybody would be doing functional programming. Because what was going to happen was people weren't going to be able to write sequential programs that would run on this special purpose parallel hardware that we needed because we weren't going to be able to get things to go any faster.
Okay, got it.
So yeah, that was the point there.
Hi. Not so much a question, but about fudgets. I spent the first year of my PhD looking at things like this.
Right.
I work on arrows and Yampa. And one of the things that we saw with approaches like this is that they don't scale so well in terms of modularity when you have hundreds and thousands of fudgets or widgets.
Okay.
Because essentially what happens is to define your fudget, you need its input. And if you have a circularity, if you have fudgets that depend on fudgets, they depend on each other and they need to be defined in the same scope, which means that you can't actually separate things so much in your code. So in Yampa, we have programs with hundreds of, like proc block, arrow blocks with hundreds and thousands of lines because we can't actually separate things. If someone finds a solution to this, I'd be really interested to know.
That's very interesting. Thank you.
Anyone else?
Thank you for the great talk. Actually, I learned something about the early history of Haskell, so that's nice to know.
Good,
I would like to know what's your opinion on laziness in Haskell, and if you would do Haskell like again, would you make the same choices about laziness?
It's really tricky, isn't it? I'm teaching a course at the moment on compiler construction using OCaml, and there are bits of that where you really want laziness. So, I don't know. I don't. I suppose there's an argument that says if you had a lazy library within OCaml, maybe that would starting strict and going into lazy might be a more amenable way of doing things than the other way around. I was struck by what Stephen said this morning, that there was a bit of his code that was lazy, and it was really nice to have that laziness because you could avoid doing some computation, but everything else you wanted to switch on strict. And I think that reflects perhaps how things are for many people. I don't know. I mean, it's hard to tell. Yeah, don't know.